Alright, this video is for AP Stats, and it is the Cumulative AP Practice Test 1. It is found on pages 276 through like 280. It's the end of Chapter 4, and it reviews Chapters 1, 2, 3, and 4. Alright, starting with 1. It says, you look at real estate ads for houses in Sarasota, Florida. Okay, so we're talking real estate, home values. Many houses range from $200,000 to $400,000 in price. The few houses on the water, however, have prices up to $15 million. Which of the following statements best describes the distribution of some home prices? Which means that we have outliers to the right. Okay, so when we have outliers to the right, and house values in general are going to be skewed right, our mean is going to be greater than our median. Okay, so our mean is going to be greater than our median, and we are going to be skewed to the right. Okay, so mean greater than median. Okay. Distribution is skewed left, no. Distribution roughly symmetric, no. Distribution is most likely skewed right, and the mean is greater than the median, yes, D. Okay, so 1 is D. All right, a child is 40 inches tall, which places her at the 90th percentile of all children of similar age. The heights for children of this age form an approximately normal distribution. With a mean of 38 based on this information. What is the standard deviation of the heights of all children of this age? Okay, so here we have normal curve. Okay, the 90th percentile means that they are here. The area of this is 0.9, okay, and that value is 40. Okay, what we also know is that the mean at the center, okay, x bar is 38. I know the probability to the left is 0.9. If I do that, I end up with a z-value, okay, and that z-value we can do right now. I run this in the app, and I say I know that 0.9 is to the left, okay, and from here I now know that the z-value is 1.28, and if I use the z formula, z equals x minus x bar over standard deviation. Okay, I don't know standard deviation, but I know the z is 1.28. I now know that the value is 40. I know that x bar is 38, and I don't know s of x. So I essentially have 1.28 over 1 equals 2 over s of x, and I cross multiply and divide. If I cross multiply and divide from here, I find that s is 1.56. And looking at my possible values, it's E. All right, question 3. And by the way, I don't ask for questions where you have to find the standard deviation. Okay, that was more difficult than what I would do. But you should be able to get to a z-value from here knowing that you're in the 90th percentile. And you should, if you know all the pieces, you should be able to use some algebra to get down to 1.56. So more likely what I would do is I would ask you, I would give you the mean and the standard deviation and ask you what this value is, 40. So I would do it a little bit more straightforward than what this one did. Okay, which would allow you to use the app in that area. A large set of test scores has a mean of 60 and standard deviation of 18. If each score is doubled, then the 5 is subtracted from the result. The mean and standard deviation of the new scores are what? Okay, so when you double it, you're going to multiply by 2, and multiplying affects the 60 and the 18. So when you times by 2, they both times by 2. So we end up with 120. We end up with 36. The next one says 5 is subtracted, and subtracting 5 only affects the center. So this goes to 115, and this is 36. So 115 and 36, okay, is B. All right, next. For certain experiment, the available experimental units are 8 rats. 4 are female and 4 are male, and they've numbered the females 1 to 4, the males 1 to 4. There are to be 4 treatment groups, A, B, C, D. If a randomized block design is used with the experimental units blocked by gender, and what that means is that you would block because you would expect large variability, and you could reduce that variability by splitting it off into separate groups. So they expect females and males to be different according to these treatments, and they want to separate the females and separate the males. That way that it's kind of 2 studies, and therefore we've limited the variability for all females and all males, whereas if we grouped them all together, we get a whole bunch more variability. Okay, which of the following assignments of treatments is impossible? So we're looking for something that would not work, and if you're grouping, you should assign a treatment A to a male and a female, and a B to a male and a female, and so on. Okay, so in ours, we're going to have C as the one that doesn't work, and it doesn't work because they've got female, female receiving B, so you don't have one of each, and they've got male and male receiving D, so C does not work. All right, 5, a biology project, you measure the weight in grams G, the tail length in millimeters M of a group of mice, so they're comparing the weight to the length of the tail. The equation is this, okay, so we've got the tail length equals 20 plus 3 times the weight. Which of the following is not correct? Okay, for number 5. It says the slope is 3, okay, true, which indicates that a mouse's weight should increase by about 3 grams for each additional millimeter of tail length. No, that is not what it says. We were taking weight and timesing 3, so they've got this backwards. It would be about 3 per gram, okay, and it increases about 3 millimeters for each additional gram. Okay, so because 3 is multiplied by weight, A is the one that does not make sense. That one's kind of tricky as well. Okay, let me see the other ones. The predicted length of a mouse that weighs 38 is 134. So you take 38, plug it in here, multiply by 3, add 20, 134, yes. Okay, looking at the next ones that they have there. They now have, by looking at the equation for the least squares, you can see that the correlation between weight and tail length is positive. Well, the correlation will be positive if the slope is positive, and the slope is positive, so that's fine. If you had measured the tail length in centimeters instead of millimeters, the slope of the regression line would have been 3/10 and equals 0.3. Okay, so how do we go from, and again, millimeters to centimeters means that we have to multiply by 3, okay? And that would make this then divide by 3. So that is true. Okay. Next, one mouse weighed 29 grams and had a tail length of 100 millimeters. The residual for this mouse is -7. Okay, so what you do is you take 29, you plug it in for weight, okay, and you end up with a value. Okay, and the formula for residual is that we take y minus y hat. Okay, so if I take the actual value, which is 100, and subtract the predicted value, in this case it looks like it's going to be 107, we end up with -7. So it would be 100 minus 107, and we'd end up with -7. So the residual, which means the error for that prediction, is -7. And that is correct. So the one that didn't work out was A. All right, AP 1.6. The figure below shows a normal density curve. Okay, which of the following gives the best estimates for the mean and standard deviation? This one's pretty important. Okay, so we've had some ones that were pretty tricky just a minute ago, and what we were going to see here is that the peak, bringing it straight down, okay, is at 225, and if I'm looking where the curvature changes, okay, it's going to change about right there. Okay, and if I bring that down, okay, and I'm somewhere 225 to 275, so I'm saying it's about 50. Okay, so I'm saying this one is C. The mean is 225 where it's centered. I went to where the curvature changed, brought it down, and it was about 275. The distance there is 50. Okay, 7. The owner of a chain of supermarkets notices there's a positive correlation between the sales of beer and the sales of ice cream over the course of the previous year. Okay, so positive correlation means that as one goes up, the other goes up. During seasons when sales of beer were above average, sales of ice cream also tended to be above average. So one goes up, the other goes up. Likewise, when the sales of beer were below average, sales of ice cream also tended to be below average. Which of the following would be a valid conclusion from these facts? Okay, it says sales records must be in error. There should be no association between beer and ice cream sales. Okay, we don't know that. B, evidently for a significant portion of customers of these supermarkets, drinking beer causes, okay, no matter what, that's not it, causes a desire for ice cream. No. A scatter plot of monthly ice cream sales versus monthly beer sales would show a straight line, describes the pattern in the plot, but would have to be a horizontal line. Okay, a horizontal line is like this, and that is not what we would call a positive association. Okay, so that's not it. There's a clear negative association. Okay, they said as one goes up, the other goes up, so that's not it. So it's got to be E. The positive correlation is most likely a result of the lurking variable temperature. Remember that a lurking variable is a third thing going on in the background, causing the other two to change. That is, as temperatures increase, so do both beer sales and ice cream sales. So we're talking in the summer. So beer and ice cream sales go up in the summer as temperature goes up. That is true. E. All right. So the one doesn't cause the other. There's a third factor going on in the background. We call that the lurking variable. Number 8. Here are the IQ scores of 10 randomly chosen 5th grade students. Got it? All right. Which of the following about this data set is not true? Okay. And what we're talking about is basically the basic stats. And this one's really important. So make sure you are able to do this one completely. And they said which one is not true. And the one that is not true for this one is E. Okay, if the value 96 were removed from the data set, the interquartile range of the remaining 9 scores would be lower than the IQR of all 10 IQ scores. Okay, so that is the one that is not true. So how would you actually answer this? You'd type all these values into L1 and you'd run basic stats. And then you'd look down each one, and all of these are true except for E. Now, how do you test E? What I would do is I would remove the 96, okay, and then I would test it again and see if the interquartile range actually changed to a smaller number, because that was the claim that they made, and that is not true. All right, 9. Before he goes off to bed each night, Mr. Clean pours dishwasher powder into his dishwasher and turns it on. Okay, from the examination of the data, he concludes that Mr. Clean dispenses a rather consistent amount of powder each night. Which of the following statements is true? Okay, so one says there's a high positive correlation between the number of days that have passed since the box was opened and the amount that is left in the box. So what that means is a high positive correlation would say this: as days goes up, the amount of powder, let's just say weight, in ounces, goes up, and that doesn't make sense. Okay, so he's using the stuff over time, so you would expect a dropping, not a positive correlation, a negative correlation. So 1 doesn't make sense. A scatter plot with days since the purchase as the explanatory variable and the amount of dishwasher used would show a strong positive association. So the amount used, okay, that would look like days, and the amount that has been used, you start off at 0, okay, because you haven't used any, and then it rises. So the amount you've actually used would go up. So yes, that makes sense. No, it did not make sense here. Okay, so this was the amount remaining. This is the amount used. So the amount used goes up, remaining does not. Remaining should do this. All right, and then 3, the correlation between the amount of powder left in the box and the amount of powder used, so that's this one, should be -1. One more time. The correlation between the amount of powder left in, okay, let's do that one. That one's different. All right, the amount of powder left, okay, and the amount used, okay, should be -1. Let's see. So when you buy it, okay, you've got a lot left and nothing used, okay? And when you've, I probably should have reversed these two, which doesn't really matter. Okay, so when you've used it all, you have nothing left. And every time you use something, okay, you would expect that, for example, if you had 60, okay, in the box to start, and then you'd have 60 that you could use, you're going to find that if you use 10, so you're at 50 here, then 10 is that point there. So you're going to find that these are always right on that line. Okay, so that would be a -1 slope. Okay, so that does make sense, but that's kind of hard to visualize. All right, so for number 9, we're going to find 2 and 3. Okay, so 2 and 3 are the ones that make sense. So I said no to number 1, yes to 2, yes to 3. Okay, so I tried to draw graphs of those. The third graph was kind of difficult. Okay, so that was kind of an AP style question that was pretty tough. All right, the General Social Survey conducted by the National Opinion Research Center at a University of Chicago is a major source of data on social attitudes in the United States. Once each year, 1,500 adults are interviewed in their homes all across the country. The subjects are asked their opinions about sex and marriage, attitudes towards women, welfare, foreign policy, and many other issues. The GSS begins by selecting a sample of countries from the 3,000 countries in counties in the country. The counties are divided into urban, rural, and suburban. A separate sample is chosen at random from each group. Okay, this is all right, so really we are organizing the data according to what we're saying is the urban, the rural, and the suburban. Okay, so here is the actual way in which they're being organized. Okay, so it matters. Now, we're between a cluster sample and a stratified. Okay, so looking at all the options, we see that the other options here are cluster, okay, stratified, and volunteer response. Okay, so we are definitely not A, B, and E. We're down to C and D. Now, a cluster, the purpose of doing that is that all clusters are the same. All clusters are the same, and the individuals are different. In a stratified, we're going to find that the strata, so strata, are different, but the individuals in it are the same. Now, what they've done in our case is they've split counties as urban, rural, and suburban, okay? Which means they don't have exactly the same types of groups. They have 3 different types of groups. And we would expect that those in the urban county are similar to each other, but not similar to those in the rural. And those in the rural, same thing. This one is similar to the other rurals, but not the same as the urbans. Okay, so those in the group are the same, and the groups themselves are not the same. Okay, that's kind of difficult. Okay, all right. Number 11. You are planning an experiment to determine the effect of brand of gasoline and the weight of a car on gas mileage measured in miles per gallon. Okay. You will use a single test car adding weights so that the total weight is 3,000, 3,500, and 4,000 pounds. The car will drive on a test track at each weight using each of Amoco, Marathon, and Speedway gasoline. Which is the best way to organize the study? Okay, so looking through this, start with 3,000 pounds, okay, then do 3,500 and 4,000, change to the other gas, okay, and then do the 3 weights again, okay, and so on. So that's not bad. All right, so that one's okay. What they don't have there is repeated samples at each weight and gasoline, okay? Start with 3,000 pounds in Amoco and run the car on the test track, then change to Marathon. That seems unreasonable. You wouldn't want the 3,000 to stay the same and then switch gasolines, okay? So it's way more reasonable to use a gasoline at 3 different weights, okay, and so on, all right? So this one does not seem reasonable at all. Choose a gasoline at random, then run the car at all 3 weights. In order, choose one of the 2 remaining gasolines at random. Again, run the car at all 3 weights. Do the same for the last gasoline. So you have 1 sample at each different thing. Okay, so that's not terrible. But it is, again, it's only 1 sample. So they're not really replicating enough. There's not a ton of data. The sample size is pretty small. All right, there are 9 combinations of weight, which is true. We've got 3 weights and 3 gases. 3 times 3 is 9. Okay, so there are 3 combinations. Run the car several times using each of the combinations. Make all these runs in random order. Okay, so we randomized in terms of the order. Okay, so we've got random assignments and all these things. Everything is there. We've looked at every possible way, and we've done it multiple times each. Okay, randomly select an amount of weight and a brand of gasoline, then run the car on the test track. Repeat this process 30 times. Well, then you didn't try it for everything. So D is the one that makes sense. And that goes with Chapter 4. All right, a linear regression was performed using the 5 following data points. So I've got them. The residual for which of the 5 points has the largest absolute value. Okay, so absolute value means furthest from its actual prediction. So you've got to do a couple things. The first thing you've got to do here is you have to find the actual regression equation. So let's do that. When you type in these in 12, when you type in these ordered pairs, okay, into your L1, L2, L1, L2, and so on, and you run the linear regression, you find that your predicted y is equal to negative 1.6x plus 23.6. Okay, so slope negative 1.6 and your y-intercept of 23.6. All right, so there it is. These are the actual values, 22. To find the actual predicted value, you take 2 and you plug it into this formula for x. Now, when you do that, you end up with, when you take 2 and plug it in, you end up with 20.4, okay? And remember that your residual is equal to y minus y hat. So I would then take 22, I would subtract the 20.4, okay? And I'd end up at 1.6. So 20.4, subtract the actual value of a of 22 gives, the actual value 22 minus the 20.4 gives 1.6. All right, the next one, if I take 10, okay, and I take 10 and I plug it in, I end up with a value of 7.6. Okay, so if I take 4 and I subtract 7.6, I end up with a negative 3.6. So its residual is here. So here I've got y hat shown there, and I've got my residual showing here. And you do that for each value, and you look for which one is the furthest away from 0. They said absolute difference. And the one that's going to be the furthest away is going to be B. Okay, so B is the one that's the furthest away. Okay, 13. The frequency table below summarizes the times in the last month that patients in an emergency room of a small hospital waited to receive medical attention. Okay, and so you've got less than 10 minutes occurred 5 times and so on. Which of the following represents possible values for the mean median waiting times for the emergency room? Okay, so first, I'm going to see that how many are in here total. We don't know that. Okay, so I've got 5, 24, 45, 38, 19, and so on. So I'm going to figure out, just ballpark, around what the median is going to be. Okay, so 5, I'm going to add to that 5 plus 24 plus 45 plus 38 plus 19 plus 7 plus 2. And I find that there's 140 total things there. Okay, so half of that is 70. So how soon until I get to 70? So if I go 5 plus 24, I'm at 29 plus 45. Okay, now I'm at 74. So somewhere the 70th value occurs somewhere in here. I know my median has to be somewhere in the 20 to 30 range. Okay, so my median's in the 20 to 30 range, which means I'm down to 27 and 28. Okay, so which one would I expect for the mean? Now, if you look at the skew, we are skewed to the larger numbers. Okay, so we've got values at the high end, and that would pull the mean in this direction. Okay, so again, the skew low to high, we would be centered somewhere in here, and then it tails off to the large values, and therefore the mean is going to be larger than the median. Okay, so 13's answer is B. All right, box plots are shown below. Based on the box plot, which statement below is true? The spread of both plots is about the same. Okay. Next, the means of both plots are approximately equal. Okay. It does not appear that the means are going to be approximately equal. Which one is true? Okay, so I would say that the spread's both about the same. The range is about the same, and the interquartile ranges are not that far off. Okay, so A is leading the way right now. The means are not the same. Plot 2 contains more data. We don't know. The medians are approximately equal. No. Median, not the same. Plot 1 is more symmetric than plot 2. Okay, plot 1 is more symmetric than plot 2. No. I would say that this box has the median too far to the left. This one is more centered. Okay, so I'd say that plot 2 is better. So A is the one that's the most true. Okay, again, that's kind of tough. That's the way these AP questions kind of fall. All right, last area. The manufacturer of exercise machines for fitness centers has designed 2 elliptical machines that are meant to increase cardiovascular fitness. The 2 machines are being tested on 30 volunteers at a fitness center near the company's headquarters. Okay, so first I'm underlining volunteers. The volunteers are randomly assigned to one of 2 machines and use it daily for 2 months. All right, so they've got random assignment, but they still have volunteers. A measure of cardiovascular fitness is administered at the start of the experiment and again at the end. The following table contains the difference in the 2 scores, so after minus before. So if they improved, we would see a positive value. If they had not improved, if they'd if they just didn't improve at all, we would see a 0, and if they got worse, we would see a negative, so after minus before. All right, so what we're seeing in this data now, okay, for the two machines, know that the higher scores indicate larger gains in fitness. Got it. Okay. Write a few sentences comparing the distributions of the cardiovascular fitness gains from the two elliptical machines. Okay, describing the distribution means basically you should describe the center, all right, and the center looks greater for machine B, okay, and describe the spread. The spread looks greater for machine B as well. So machine B had a greater center, so it looks like it's further up the ladder here. But at the same time, it looks like it's more spread out. So there's more variation in B. So A is less variable, but it doesn't look like its highs are as high as machine B. Okay, and what else? The shape. I would say that A looks very bell-shaped and symmetric, whereas B looks like it is skewed to the left, skewed to the small numbers. So we've got lumps here and then skewed over there. Okay, all right, and outliers. So any outliers that occur, nothing is really jumping out at me as like being way far away from the data. So maybe the 2, this person that's a 2 is pretty far away, so that's potential. Okay, but there's no outliers definitely in machine A. Okay, so just going by looks, that's what I see. We could also type in every single one of these values into L1, every single one of these values in L2, and we would know precisely what those values are. Okay, so just make sure distribution describes the center, the shape, the spread, and the outliers. Which machine should be chosen if the company wants to advertise it as achieving the highest overall gain in cardiovascular fitness? Explain your reasoning. Well, I'm going to choose machine B because its mean, its median, and its maximum are all going to be greater. Okay. Which machine should be chosen if the company wants to advertise it as achieving the most consistent gains? Consistency is about variability. Machine A is more consistent. Okay, so if you want to know what you're going to get, machine A is going to be better. So it has a smaller standard deviation range and interquartile range. So machine A. Part D. Give one reason why the advertising claims of the company, the scope of inference for this experiment would be limited. Explain how the company could broaden that scope of inference. Okay, so they cannot really generalize to the population because they have volunteers. So using volunteers makes it so that you cannot generalize to the larger group. So if they want to increase their scope of inference, they need to get random volunteers, not volunteers, random selection from the population. Okay, that's how they would increase their scope. All right, 16. Those who advocate for monetary incentives in a work environment claim that this type of incentive has the greatest appeal because it allows the winners to do what they want with their winnings. Those in favor of tangible incentives argue that money lacks the emotional appeal. Say a weekend for two at a romantic country inn or an elegant hotel or a week-long trip in Europe would be better. All right, a few years ago, a national tire company, in an effort to improve sales of a new line of tires, decided to test which method, offering cash incentives or offering non-cash prizes such as vacations, was more successful in increasing sales. The company had 60 retail sales districts of various sizes across the country and data on the previous sales volume for each district. Describe a completely randomized design using 60 retail districts that would help answer this question. What I would do is I would put all 60 retail districts into a hat on slips of paper. Okay, and so I would randomly draw that out. So that's random selection. Now I need to randomly administer the treatment. So there's 2 treatments, so we might as well flip a coin. So when you flip a coin, if it comes up heads, I would say that heads would be the money incentive, and tails on the coin means that that selected district would be potentially receiving the tangible, like the vacation. All right, B. Explain how it used the table of random digits below to do the randomization that your design requires. Then use your method to assign treatments to the first 3 experimental units. Show your work clearly. Okay, so since they're using a table, what we could do is we could have all of those numbered, let's say numbered 1 to 60, okay? And the first 30 that we draw, or first 30 numbers that are going to be drawn without repeat would be given the cash, okay? So we would say that number 7 is cash. Okay, number 51 is cash. Number 18 is cash, and so on. Okay, so the first ones to be given cash were 7, 51, and 18. And you would just keep that process going. 89 we would skip, okay, so 89 out. 15 would be the next one, and so on. And we would do that until we had 30 unique stores or districts that we would use then to be the cash incentive. And those that were not selected, the ones not in the first 30 to show up, would be given the other incentive. So there's another way to do it. All right, one of the company's officers suggests that it would be better to use a matched pair design instead of completely randomized design. Explain how you would change your design to accomplish this. Okay, there's two ways you could do that. Okay, the first way is that you would try to pair up stores to be as identical as possible. So you could look at the demographics of where they are. Are they in a country district? Are they in an urban district? Are they having good sales? Are they having bad sales? How large are they? You could pair them up as best you can, okay? And then you'd have one of those randomly assigned to the cash and one of those randomly assigned to the vacation incentive or the tangible. And then you would just compare those two at the end. A better way to do it would be to take every district and flip a coin and then have that district be on either cash or tangible, randomly assigned through the coin. And you would do that for, let's say, 2 to 3 months, okay? And then that same store would then flip incentives to the second way. So if they were first on cash, now they're on tangible. If they're first on tangible, now they're on cash. And then you can compare that store to itself. So now you've completely reduced variability from store to store. What you haven't done is reduce the variability from time of year. So hopefully you get some of that by half of them or so being on early cash and half on later cash. So again, that's probably the best way to do it. But they would both be acceptable ways to describe matched pairs. All right, last one. In a retail stores, there's a lot of competition for shelf space. Not only are there national brands for most products, but most stores have their own in-house brands. Since shelf space is not infinite, the question of how many linear feet to allocate to each product and which shelf, top, bottom, or somewhere in the middle, to put it on. The middle shelf is the most popular and lucrative since most shoppers, if undecided, will simply pick the product that is at eye level. The local store that sells many upscale goods is trying to determine how much shelf space to allocate to its brand of men's personal grooming products, so like deodorant. The middle shelf space is randomly, the middle shelf space is randomly varied between 3 and 6 linear feet over the next 12 weeks. The weekly sales revenue in dollars from the store's brand of personal grooming products for men is recorded. Below is some of the computer output from the study along with a scatter plot. Okay, so the shelf length, okay, and then sales dollars. Okay, so it appears that the more shelf length that is given, the more sales dollars come in. All right. Does it appear that the weekly sales revenue is related to the shelf length allocated to the house? Justify your answer. Yes. It appears that there is a positive linear association between shelf length and sales. Okay, so yes. All right, I would say that there is evidence from the scatter plot, okay, that we have a positive linear association. Okay, all right. And how confident am I? That looks pretty strong, and our R value, our R squared value is 98%. Okay, so 98% is super high. And if I wanted to know the actual R value of that, I just square root that value. So if I take R, let's see, the second square root 0.982, it's a 0.991. Okay, so the R value is 0.991. Got it. Okay, so it is a very, very strong linear association. Write an equation for the least squares regression line. Be sure to define any variables that you use. Okay. And I'm going to see that I have sales hat equals 318, okay, is going to then add to that 153 multiplied by length. Here we go. Okay, interpret the value of S. S is the standard deviation of the residuals, okay, so the average distance away from the mean, of the predictor was 22. Okay, so that'd be 22 looks like dollars. All right. Identify, interpret the coefficient of determination. R squared is the coefficient of determination. It says that 98% of the variation in sales is accounted for by the line. Okay, so a linear line predicts 98% of the change in sales dollars. Okay, and F says the store manager questions the intercept of the regression line. Am I supposed to believe that this analysis tells me that I can sell these products with no shelf space? How do you answer her? Okay, so first of all, they are correct. If you took length down to 0, it says that you'd have $318 worth of sales. The problem with that is that it's not meaningful. All the data is between 3 and 6. Okay, so that is interpolation to be inside of this data set. Once I'm that far either to the left or to the right, okay, I have become unpredictable. All right, so we can't use this line too far outside of the data set that is provided. So it is not meaningful to take this shelf length down to 0. It's too far away from the data collected.